Okay, so now we are in business, I think. Share. Okay, sorry about that. Those of you online, I'm sorry about the hiccup. I'm just going to quickly start over. We didn't cover much. So this is where I started. So I was mentioning that, of course, in the course of performing experiments, you'd have to take measurements using different instruments and so on. And I was making reference to the metric system as a system that is used universally as scientists to record measurements, right? Or to express the units of the particular measurement that you're making. The reason why the metric system is used worldwide is because it's very convenient, especially when it comes to dealing with very large or very small numbers. So the example I gave is, for example, the dimensions of an atom. As you can imagine, that's very small. And also, if you're looking at large numbers representing, for example, the distance between the moon and the Earth or the mass of a planet, then we can find the metric system useful also for expressing those measurements. So what we have here on this page is a small sampling of the different types of prefixes associated with the metric unit. So you use these prefixes along with the base units to basically express a particular unit of a particular measured value. And I was saying to the group here in the classroom that the table that I provided for you guys, which is this table right here, also includes 2 pages which contains pretty much all the prefixes that you're going to use. So this is more comprehensive than the one that I showed you earlier, right? These are the ones representing the smaller prefixes. So you use this in conjunction with the base unit. And the example I think I gave was the relationship between the meter unit and the decimeter. So 1 decimeter is equal to 0.1 meters because deci means 0.1, which is the same thing as 10 to the minus 1 meters, for example, right? And then the next page has larger prefixes, right? So again, just to use a quick example, kilo means 1,000, so 1 kilogram is equal to 1,000 grams because the kilo prefix is equal to 1,000, all right? So that's how we use the prefixes along with the base unit to express units in the metric system. So let me go back to the PowerPoint and let me skip all this. So the first type of measurement we're going to talk about here would be length, and then associated with that would be area. But let's talk about length first, right? So according to the metric system, the base unit is the meter unit. And the meter, if you compare it to a yard, is a little longer. If I remember correctly, 1 meter is equal to 1.096 yards. I could be wrong, but I think that's what it is. You can check, of course, in the tables that I've just showed you, all right? And then there are some derived units based on a combination of the prefix and the base unit. So I mentioned this one earlier. 1 kilometer is equal to 1,000 meters. And just to give an idea, comparison to the non-metric system, that's about 2/3 of a mile. Centi means 100, so 1 centimeter is equal to 100th or 0.01 of a meter. And milli means 1,000, so therefore 1 millimeter is equal to 1,000th or 0.001 of a meter. And just to give you a feel for what we're talking about here in terms of these measurements, a contact lens is about 1 centimeter in diameter and about 1 millimeter thick. All right, so that gives you an idea as to the type of values we're looking at. And associated with area is actually associated with length to some degree, because what you'll find is that the unit of an area can be expressed, and is usually expressed as the square of the unit of length. So if the unit of length is meters, then the unit of area can be expressed as meters squared, all right? So that's the relationship between the area unit and the length unit. Basically, the area unit can be expressed as a unit of length squared. Okay, and then there's another unit with respect to the volume, which is also related to length, right? Now, by definition, the volume is the amount of space that is taken up by an object, right? And the derived unit of volume is the meter cube unit, okay? However, there is another unit which is not a derived unit of length, which is oftentimes used as a metric unit, and that is the liter unit, symbolized by uppercase L, all right? And there's a relationship, of course, between, if you're going to use a liter unit as if it's a metric unit, then we can use the prefixes as well to get smaller or larger unit values. So for example, 1 milliliter is the same thing as 0.001 liters, right? There's also another unit which is actually directly related to length. It's derived, the centimeter cube, a centimeter cube unit, I'm sorry. So the centimeter cube unit is actually the same as 1 milliliter, right? So 1 milliliter is equal to 1 centimeter cube, all right? And just to give an idea as to what we're talking about here in terms of the volume, in a teaspoon, there are about 5 mils of liquid that you can pour into a teaspoon. Now, this diagram here is basically showing you the relationship between different units. Some of them derived, some of them not, right? So basically what we have here is a large cube where it is 10 by 10 by 10 centimeters in terms of its dimensions. And if you can imagine this large cube made up of smaller cubes, each of them with a 1 centimeter edge length. So what does that mean? That means that each of the smaller cube would have a volume of 1 centimeter cube, right? So if you can stack them up in the way that is shown here, where you basically, you form a base here with the cubes and then you form another layer and so on until you get to the total length here being 10 centimeters, then what you'll find is that the total number of cubes, the smaller ones that you're going to need will be 1,000 of them in order to make the larger cube, right? So basically, we can say that, hold on. I'm going to start off by saying that 1,000 cm cube, right, is equal to 1,000 mils, as we said before, all right? Now, in the case of the cm unit, we know that 1 centimeter is equal to 10 decimeters, or the other way around, actually. 10 centimeters is equal to 1 decimeters, all right? So if that is true, then 1,000 centimeters cubed would be the same thing as 10 centimeters raised to the third power, which would be equal to 1 decimeter raised to the third power, which is equal to 1 decimeters cubed, right? And we know that milli means 1,000, so therefore this would be equal to 1 liter. So therefore, as a result, we can conclude that 1 liter is the same thing as 1 decimeters cubed, which is stated right here, right? So basically, the decimeter cube unit is the same thing as a liter unit, and the milliliter unit is the same thing as a centimeter cube unit, right? So I'm just showing you some different relationships between the different units as far as volume measurements is concerned. Okay, another unit we can look at is mass and time. Let's look at mass first. People in everyday language tend to confuse the terms mass and weight as if they mean the same thing, right? But they're not the same thing, technically speaking. Mass is the amount of material that is present in an object, while the weight is the force of gravity that acts on a mass, right? So things that have a greater mass would be heavier, all right? Of course, one can tell the difference between mass and weight if you were to take an object and weight here on Earth, and then you take that same object to, let's say, the moon, and the weight will be different, even though the mass is the same. So that shows you that there's a difference between mass and weight, all right? So as I said before, mass is the amount of material that is present in an object, and the base unit is a kilogram unit, which is a combination of a prefix, which is kilo, and the gram unit, which is a base unit in the metric system, all right? So as we said before, 1 kilogram is equal to 1,000 grams, all right? So just to give an idea as to what we're talking about here, a 1 liter bottle of soft drinks has a mass of about 1 kilograms, all right? And there's some other units that are commonly used as well. You have the milligram unit, you have the gram units, and so on and so forth, all right? Now, as far as time is concerned, the base unit of time is the second unit. But of course, in science, and because of that, we can use the metric prefixes along with the base units, such as micro, nano, and so on, and milli, all right? However, in science, we also use, and this is one of the few areas where we don't really stick to the metric system, because we often use in science other units that we're accustomed to: minutes, hours, days, and years, all right? So those are the units of time that we oftentimes use when it comes to the measure of time, all right? And then we get to the temperature measurement. Temperature, simply put, and this is a very simplified definition of temperature, it is the amount of the intensity of heat that an object will have. And as stated here, that is a property that tells you the direction that heat will flow. In other words, if you have two objects connected to each other, and one is hotter than the other one, then the heat flow would be from the hotter object to the cooler object. That always happens, right? So that's what temperature is all about. Now, it turns out that in the sciences, the metric system used for expressing the unit of temperature is Kelvin. But also, again, this is one of those instances where we use other units when it comes to measuring of temperature. The most common one would be the Celsius unit, right? And the Celsius unit is based on the temperature, not the temperature, the properties of water, right? We all know that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius, right? So what was decided by the powers that be was that the freezing point of water was decided to be made 0 degrees, and the boiling point of water was decided to be 100 degrees. So basically, once you set those two values, then you end up with a scale resulting from that, all right? So that's basically how we came up with the Celsius scale, which is also called the centigrade scale. And then there's another scale, which is used primarily in the United States when it comes to weather reporting. If you were to travel to some other country like Canada, their weather reports, you see that the temperature would be expressed in Celsius, right? And my understanding is that United States is the only country where they, in their weather reports, express the temperature in units of Fahrenheit, right?
There's like 2 other countries.
Oh, really?
I want to say there's like 2 in South America. I think.
Oh, really? I'll have to look that up.
I think Peru is one of them.
Oh, okay. I'll look that up and see. But as far as I know, United States is the only country that, when they report their weather on TV and so on, they express it in Fahrenheit. Anyway, so those are the 3 major units of temperature. So there are relationships between these different units, right? So this equation here that I've made up here shows you the relationship between the temperature in Fahrenheit and the temperature in Celsius, right? TF, which is the temperature in Fahrenheit, is equal to 9 degrees Fahrenheit over 5 degrees Celsius times the temperature in Celsius plus 32 degrees Fahrenheit, right? So that's the relationship between the Fahrenheit temperature and the Celsius temperature. So if you want to find the temperature in Fahrenheit, you simply plug the value here in for the temperature in Celsius, and that gives you the temperature in Fahrenheit. Now, if you want to do the reverse, right? In other words, if you're given a temperature in Fahrenheit and you want to convert it to Celsius, then of course you have to do some algebraic manipulation of this equation here. So when you do that, you're going to end up with this equation where the temperature in Celsius is equal to 5 degrees Celsius times the temperature in Fahrenheit minus 32 over 9 degrees Fahrenheit, right? And then in terms of the relationship between the temperature in Kelvin and the temperature in Celsius, unfortunately, I did not include it here in the slide, so I've written it right here. TK is the temperature in Kelvin. Whoops, sorry. TK is the temperature in Kelvin, and that is equal to 1 over K. 1K over 1 degree Celsius times TC plus 273 Kelvin, and that gives you the equivalent value of the temperature in Kelvin, if you're given the value in Celsius. Yes, sir.
So it says we often use Celsius for scientific work.
Mm-hmm.
In
Well, mostly Kelvin, but often Celsius, yeah.
Right, okay, so most of it is going to be using Kelvin?
If you go to any literature in science, it's mostly Kelvin.
Okay, because that kind of confused me, because last year in intro to chem,
Mhm.
we would, it was mostly when we were dealing with gas laws.
Okay. Yeah, well, those have to be in Kelvin.
Right, we were always told to give our.
Exactly, right.
We'd be given like our temperature would be given in Celsius, we have.
It all depends on how the question is worded.
Right,
The question could give you the temperature in Celsius. And like in the case of gas laws, as we're going to see later on in chapter 5, yes, you're gonna have to convert all those temperatures to Kelvin.
so in this class, it'll also be in Kelvin?
Yeah.
Okay,
Now, there are some instances where you don't need to. Like, for example, I'm thinking of questions dealing with specific heat. In some cases, you don't need to, in those situations, you don't need to convert to Kelvin. You can if you want to, won't make a difference, but you don't need to. All right.
gotcha.
But in the case of gas laws, you need to, definitely. All right. And there's a reason for that, which we'll get into when we get to chapter 5. Okay, continuing. Okay, so before I leave this page, this diagram here basically shows you two thermometers, one that is calibrated in Celsius and the other one that is calibrated in degrees Fahrenheit. And there's a side-by-side comparison between these two. Most thermometers, including the one that we have in our labs, they have both scales on them, right? But in some cases, I've seen where some thermometers have only one type of scale, right? And this is just comparing the temperatures for different, situations. For example, the freezing point of water, as I said before, is 0 degrees Celsius. So if you put 0 here, where the temperature TC is right here, then you're going to get the corresponding temperature in Fahrenheit being equal to 32 degrees Fahrenheit, which is what we have here on this side right here. In the case of the boiling point of water, which is 100 degrees Celsius, if you put 100 degrees Celsius here in this equation, you're going to end up with the the boiling point of water being 212 degrees Celsius, all right? And then I think what they did here was room temperature, which is about 20 degrees, give or take. If you put that here, right, then basically you're going to get the temperature expressed in Fahrenheit being about 69 degrees or so, all right? So that just shows you the relationship between the Fahrenheit scale and the Celsius scale. Okay, so here's an example, and I actually worked this example yesterday in the class that I teach at Citrus, so that's why I see these scribblings right here. So let's say you decide to go to Canada, and everything is calibrated in degrees Celsius, right? Including their room thermostat in the hotel that you're staying in, all right? So you want to keep the temperature at 72 degrees Fahrenheit because that's what you're comfortable with, right? So the question is, how would you set the thermostat in the hotel room to get the same equivalent temperature, right? So of course, the formula that we're going to use is this formula right here, right? And what we're going to do is plug 72 degrees Fahrenheit here in this where TF is. And when we do that, we end up with 72 minus 32 to give you 40 within the parentheses, and then we multiply that by 5 degrees Celsius over 9 degrees Fahrenheit, and you end up with your final answer, in this case, to be equal to 22 degrees. And that's it. So that's a relatively simple example. Hold on, let me check something here. Okay. All right, any questions about this? Any questions? Any questions? Okay, so let's talk about these two terms, precision and accuracy. People tend to use these two terms as if they mean the same thing in everyday language, but in science, they mean two different things, especially when it comes to making measurements. Okay, so let's talk about these two terms. First of all, precision. What is precision? Precision has to do with how closely repeated measurements approach one another. So let's say, for example, I gave you guys a simple task of, let's say I gave you a meter rule, and I gave you the simple task of measuring one particular desk in this room, right? So one person comes, record their measurement without telling the other person, and so on. And each of you get your values recorded. Then the precision of the measurement is referring to how close those values are to each other, right? The closer the values are to each other, the more precise the measurement is, all right? So that's what we mean by precision. Accuracy means something different. Accuracy refers to how close measured values are to the true value, all right? In other words, let's say I know accurately what the length of the desk is, then what I would do is compare your values that you would have measured to what is the true value of the length of the desk, and how close those values are is basically how accurate your measurements are, all right? So to illustrate the difference between these two terms, we're going to use these pictures right here, where we have a dartboard, right? And the middle of the dartboard represents the true value, right? And each time you throw a dart on the dartboard, that represents an attempt at measuring something, all right? So in the first case, what do we notice? We notice that somebody, whoever this person is, threw darts, and the darts are all over the place, far from each other and far from the center, right? So this represents a situation of low accuracy and low precision, all right? Now, in this case here, this person threw the darts, and the darts end up almost on top of each other, right? And at the same time, they're far from the center, right? So what does that mean? That means that the accuracy is low because the darts are nowhere near the center, but the precision is high. And this often happens when you're taking measurements using an instrument that is faulty, right? The instruments keep making the same faulty measurement each time, even though you do everything in your power to make the measurement as accurate as possible, but the instrument keeps making the same faulty reading or whatever measurement, right? So we tend to see that happening in this case right here. Now, in this case, the darts are closer to the center, but they're relatively speaking spaced out, right? So the accuracy is relatively high, but the precision is low. High because the accuracy, that is high because the darts are close to the center, but the precision is very low because the darts are spread out from each other. And then here is what we all aim for, of course, right? High accuracy, high precision, where the darts are exactly on the center. And of course, because they're on the center, they're also on top of each other as well, all right? So this is what we aim for when we are making measurements in our experiments, all right? So in the real world, we can never be absolutely certain as to whether or not the measurement we make is accurate, all right? Now, why is that so? Well, as I said before, there is assumed to be a true value for a particular measurement. The thing is that true value is subject to being questioned itself because, after all measurements are done by human beings, right? So there's always going to be some possibility of error in making a measurement, even if one takes all the precautions to make it as accurate as possible, all right? So what we do is that we make repeated measurements, right? And we strive for precision, right? Which is what the aim of the exercise I just described a while ago. If each of you take a measurement of the desk, then it's more likely that you're going to be close to accurate as opposed to being inaccurate, right? So basically, and this is especially true if the measurements are precise, if the measurements agree with each other closely. So basically, we hope, not always correctly, that good precision would imply good accuracy. And that's basically one of the limitations of the practice of science, because measurements are human endeavor. And not only can you have experimental errors, you can have other errors as well. And therefore, at best, measurements are estimates, right? So, and that's basically how things work out when it comes to making measurements, when it comes to experimentation and so on. Now, how do we reflect or express the level of precision in a measurement? We do so by writing down what is called, or determining what is called, the amount of significant figures expressed in a measured and also in a calculated value. But for now, we'll be talking about measured values. So what we're talking about is determining the number of significant digits when you're taking a measurement. So this begs the question, what do we mean by significant digits, right? Well, before we get to the definition, let's look at this example. Let's say you want to determine the mileage of a motor vehicle that you're driving, right? And you know that the volume of the motor vehicle, in terms of the volume of the gas tank, is 14.1 gallons. And let's say that you were successful in driving a total distance of 273.0 miles on a full tank of gas, right? So, of course, we all know how to calculate the mileage, right? We take the number of miles and divide it by the volume, the gallons, and we end up with, if you do your math on your calculator, you're going to end up with this string of numbers right here, right? Now, in reality, you cannot predict how far your car would go to this extent, all right? To the, how many decimal places? 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places, right? So what you have to determine is how many of these figures are significant, right? And therefore, the other figures would simply be meaningless and you can drop them from recording what your final answer is. So how do we determine the sig figs? Well, let's first define the sig figs, what they are. By definition, the significant digits are those that are known, right? Those that you can establish, certainly, plus one estimated digit. So collectively, those digits are said to be significant, all right? So let's say, for example, you're given this number, which represents pretty much any quantity. Could be the mass of something or the volume of something. Then basically, the first 5 digits you'll be certain about, and they're known. The last digit, the 3, would be an estimated digit, all right? So therefore, collectively, you have a total of 6 significant digits being expressed here, if this represents a measured value of some sort, all right? So basically, the greater the number of significant digits that is expressed in a measured value, and also in a calculated value, the more precise the measurement is, or the more precise that value is, all right? So it's a number of significant digits that we use to determine the level of precision in a measurement. Now, how do we determine which digits are significant when you're actually doing a measurement? The answer is, it depends on the instrument you're using. Now, if you're using an instrument like a thermometer or a meter rule, all right? As we all know, you have some divisions that is present, that is etched on the scale or the stem of the thermometer, for example, right? Then this is how you're going to go about showing how you measure the value to the correct number of significant figures. So we're going to look at this first example right here, all right? In this example, well, firstly, let's look at the scale. We have number 20 here, and we have number 30 here, right? And we have 10 equal divisions, right? So therefore, we know that this line represents 21, this line represents 22, and so on, right? So the question is, what is the measurement being represented by the mercury getting up to this point right here, all right? Now, we know that based on the scale, it is 21 point something. So the question is, what is that something? What is that digit that follows right after the 21 point, right? Now, a reasonable person could look at this and say, you know what? I think it is 21.1, right? Another person could look at this and say, you know what? No, I don't agree with you. I think it's 21.2, right? The point I'm getting at here is that that digit has to be estimated, right? So as far as I'm concerned, the 21.1 and the 21.2 are just as correct, because we know we're certain about the 21 part of it. What we are not certain about is what comes after the decimal point, right? So if I were to give a question like this, both persons would get the same credit, right? In actual fact, it is 21.2, but as I said before, you know, it could be 21.1. Somebody could even say it's 21.3, even though that's a bit of a stretch in my opinion. But basically, the point I'm getting at here is that at best, we just can simply estimate the digit after the decimal point, right? So therefore, we end up with 21.2. And if you look at this here, this is expressed to 3 significant figures and also to 1 decimal place, right? So that's what happens in the case of the first thermometer. In the case of the second one, you'll notice that the mercury level is at it seems to be at the 22 mark exactly, right? But because this scale is graduated in the same way as this scale, the level of precision would have to be reflected the same. In other words, you'd have to round off to the first decimal place, right? So the answer I would give for this one as to what measurement is being represented here would be 22.0. One decimal place and three significant figures, all right? Now, when we get to the third scale, you'll notice firstly that the way it's graduated is different compared to the other two, right? Because not only do we have 10 equal divisions between 20 and 30, but between 20 and 21, we have 10 equal divisions as well, right? So let's see how this affects how we determine the measurement. So I don't know if you can see from where you are, but from here, you'll notice that this is 21 and this is 22, right? So we know that it is 22 and then point what? Well, this mercury level seems to be slightly above the first mark right here, right? So basically we can conclude that this is 22.1 something, right? So again, the question is, what is that something? What is that digit after the one, which is after the decimal point? So a reasonable person could look at this and say, you know what, I think this is 22.11. Another person could say that, you know what, I think this is 22.12. Again, both persons will be right as far as I'm concerned. All right, the actual answer is 22.11. But again, I would give equal credit to students who gave 22.12, right? So this is how, based on a direct measurement, how you determine exactly the number of decimal places or the number of significant figures that you need to express your measurement in, all right? And this is something that you need to keep in mind when you're doing any experiment in any lab, including the lab courses here, right? If you're measuring the temperature of something, or if you're using a meter rule to measure the length of something, you have to take into account estimating that last significant digit so that you get the answer written to the correct number of significant figures. Now, when it comes to using instruments which provides a digital readout, no problem. You don't have the same challenges as you have here. All you have to do is just write down whatever is on the display, and that's it. And that is basically how you determine, in that case, the number of sig figs, all right? So when it comes to digital instruments like balances and so on, then that's basically how that is done. Okay, so let's talk about the rules for determining significant figures. Now, these rules are basically dealing with situations where you're doing a question and you're given values, you know, numbers representing different values in the question. Because it turns out that there are two types of numbers that you have to deal with. You have measured numbers and then you have defined numbers, right? We're going to talk about the defined numbers later on. But these rules here that we're about to discuss will be based on or dealing with measured values, all right? So the first rule is the easiest rule actually. And this rule says that all non-zero digits are significant. So all digits from 1 through 9 are significant when they appear in a measured value. So for example, if you're given this number here, 461, all those digits are significant, and therefore the number of significant digits expressed here would be 3, all right? So that's the first rule, that's the easiest rule. The other rules are a bit more complicated because the other rules have to deal with zeros in particular situations, right? So this rule says a zero is significant when it is sandwiched between non-zero digits, right? And I probably should add something here, something to the effect that it doesn't matter how many zeros, as long as you have non-zero digits on either side, then the zeros are significant. So for example, in this case here, 401, the zero here is significant, so therefore we have 3 significant digits represented here, all right? Here's another example. In this case here, you have 2 zeros sandwiched between 6 and 3, so therefore those zeros are significant, so therefore all the digits here are significant, so the total number of sig figs in this case will be 5. Here's another example. And you'll notice in the previous example and this example, you have a decimal point. That makes no difference, right? So in this case, you have a 0 sandwiched between the 3 and the 9. So therefore, the number of significant digits represented here would be 3. Okay, so that's it. So just to recap that particular rule, if you have zeros that are sandwiched between non-zero digits on either side, then those zeros are significant, all right? The next rule has to do with a situation where you have a zero at the end of a number, and there's a decimal point within that number, right? Those zeros, by the way, are significant. So here is an example of this, right? Here we have the decimal point, and we have 3 zeros at the end of this number, right? So basically, those zeros are significant, and therefore the total number of significant digits represented here would be 5. All right. I think I have another example here. Okay, so in this case here, again, decimal point. Again, we have a 0 at the end of this number. So therefore, the total number of significant figures represented here would be 5. Right? Okay, and that's it as far as the examples are concerned in that situation. So just to recap, that particular rule, if you have zeros at the end of a number and there's a decimal point anywhere in that number, then those zeros at the end are significant. All right? The next rule has to do with a situation where a 0 is not significant. And that is if that 0 or zeros appear before the first non-zero digit. All right? So here's an example. In this case here, you have 3 zeros appearing before 6, right? So therefore, according to this rule, those zeros are not significant, right? So therefore, the only significant digit represented here would be the 6. So therefore, there's only one significant digit present in this number. I think I have another example of this here. Now, in this case here, we have 2 types of zeros, right? We have the 0 that comes before the first non-zero digit, and we have a 0 that is sandwiched between 2 non-zero digits, right? So this 0 is not significant, but this 0 is, right? So therefore, the total number of significant digits here would be 3. Okay, and I think that's it for that rule. Okay, so the next rule, again, deals with a situation where a 0 is not significant. And what this rule says is that a 0 is not significant if it appears at the end of a number and there's no decimal point, right? So here's an example of that. In this case here, there's no decimal point, right? And you have 4 zeros at the end of this number. So the only significant digit here would be the 5. So therefore, there's only one significant digit represented here. All right? Here's another example. No decimal point present, and we have a 0 at the end of this number. So that 0 is not significant. So there are only 4 significant digits in this number. All right? So this is important because you'll be given questions. You're going to be given numbers representing certain measurements, and you have to take into account the number of sig figs so that you can properly deal with these numbers, especially when you're doing calculations, which is what we're going to talk about next. So basically what we're looking at, how do we deal with significant figures when it comes to mathematical operations, right? But before we do that, as promised, or as I said before, I should say, there are 2 types of numbers that you're going to deal with in science generally. You have the exact numbers and you have the measured numbers. The measured numbers, of course, are the numbers that you obtain from measurements. But when it comes to exact numbers, there are 2 types. You have defined numbers and you have counting numbers, right? And one big difference between these numbers, exact numbers and measured numbers, is that measured numbers have a finite number of significant digits, while exact numbers have an infinite number of significant figures. And that is kind of implied in the term exact. If the number represents an exact quantity, that means that basically there is no error in terms of obtaining that number, right? So therefore it has an infinite number of significant figures, okay? So just to give you some example of exact numbers, 14 people, right? The 14 is exact because all you have to do is do a head count. You don't have to measure it, right? The relationship between the meter unit and the kilometer unit, those 2 numbers, the 1,000 and the 1, are both exact numbers, right? And the reason why they're exact is because those units are related by definition, right? So all defined numbers are exact numbers. The 1,000 in the case of the meters and the 1 in the case of the kilometers in this relationship, those numbers are exact numbers. Again, counting numbers like 7 beakers, right? So in these cases, these numbers are exact, and exact numbers have an infinite number of sig figs, right? And you have to take that into account as well when you're doing any calculations, all right? So with that said, let's look at how we deal with mathematical operations, right? So of course, we're familiar with from our previous, let me see if I can get rid of this here. Oh, I can't, okay. Okay, I'm quite sure you're familiar with the four mathematical operations from your math courses. You have addition and subtraction, multiplication and division, right? Now, when it comes to applying these operations to numbers obtained by measurements and also exact numbers, you have to take into account certain rules, right? So there are certain rules when it comes to addition and subtraction, and then there are other rules when it comes to multiplication and division, right? So let's deal with multiplication and division first. When you're multiplying and or dividing numbers, right? Make sure that you round off your final answer according to the number involved in the operation with the lowest number of significant digits, all right? That's the rule that you need to apply when it comes to multiplying and or dividing any numbers, right? You make sure that the final answer is rounded off according to which of the numbers involved in the operation having the lowest number of significant figures. So I'm just going to make up an example just to illustrate this point. Let's say you are multiplying, this is going to be totally made up, 2.79 by 5.786, right? So let me get my cheat calculator here and work this out. So let's say these are two measured values. Let's say that these are meters, right? So 2.79 multiplied by 5.786. So when I did that on my calculator display, I got 16.14294. All right, so that's what I got when I put these into my calculator, right? And this would be in meters squared because you're multiplying meter by meter, right? Now, to round this off correctly, what you'd have to do is go back here and look at the number of sig figs expressed here and here. And you'll notice that this here is 3 sig figs expressed, and this is expressed to 4 sig figs. So according to this rule, what you need to do is you have to basically round this off to 3 sig figs. So when you round this off to 3 sig figs, that becomes 16.1 meters squared, all right? So that's basically what you do for multiplication and division, right? You have to round off your answer to the lowest number of sig figs of the numbers that are involved in the calculation, all right? So that's the rule for multiplication and division. If I were to divide these two numbers, I'd have to do the same thing, round off to 3 sig figs. All right. Now, the next rule has to do with the other types of mathematical operations, addition and subtraction. And basically, when you're adding and or subtracting numbers, you round off your answer according to the lowest number of decimal places of the numbers involved in the mathematical operation. So here I have an example which I used in yesterday's class in the group over at Citrus. So let's say you're adding 3.14 to 2.9, right? And if you do that on your calculator, you're going to get 6.04, right? Now, when you look at this number here, it's expressed to 2 decimal places, and this number here is expressed to 1 decimal place. So that means that you need to round this off to 1 decimal place, and that would be 6.0, right? So that's basically the rule for addition and subtraction, all right? So just to review what we just talked about here, when it comes to multiplication and division, if you're doing both of them at the same time in one particular operation, then your final answer must be rounded off to the lowest number of significant digits of the numbers involved in the calculation. If you're adding and or subtracting, then you need to round off your answer to the lowest number of decimal places. So this begs the question, what if there is a combination of operations where, let's say you did subtraction at one stage and then division at another stage? How do you deal with that situation? So let me whoops, sorry. Let me, how am I gonna do this? Oh, you know what? I don't know. Okay, let me use Word. So I'm just again create another example out of thin air. Come on. So let's say, okay, so let's say I gave you this to work out. 1.309 minus 0.213, and then I'm going to divide by 0.46. All right. So the question is, how do we determine what the correct final answer is, rounding off correctly? Now, of course, up top here, we have subtraction, right? So if you remember, the rule for subtraction is that you round off according to the lowest number of decimal places. So what I'm going to do is find out what this gives, 1.309, the top part, minus 0.213. And according to my calculation, I got 1.096. Now, according to the rules, because you have 3 decimal places here and 3 decimal places here, that means that this must be rounded off to 3 decimal places, which is what it is anyway, so we don't need to make any changes there, right? Then we divide that by the 0.46, right? And then we do that calculation. So 1.096 divided by 0.46. And on my calculator, I got 2.382608,696, right? But because we're dealing with a division now, remember the rules for division is that you round off your answer to the lowest number of significant figures, right? So up here, we have 4 sig figs. And down here, we have 2 sig figs. So that means that whatever we get here, we have to round off to 2 sig figs, which means that the final correct answer is going to be 2.4. All right? So the point I'm getting at here is that if you're doing mathematical operations, a combination of mathematical operations where the rules for one particular step is different for another particular step, you do it stepwise, right? You do the first step, you round off according to the rules for that step, and then the result of that, you take that through the next step, and you round off again, and so on. So that works when the rules are different. But when the rules are the same, you just do everything in one go, and then you round off. If it's multiplication, division, you round off according to the lowest number of sig figs. If it's addition and subtraction combination, you round off according to the lowest number of decimal places. All right? Okay. So that's basically how you deal with that situation. And again, this is something that you need to be doing in all your calculations in this course and other future courses. Okay, let me go back to PowerPoint. So the next thing we're going to talk about is, okay, so we just covered this. Okay, I wish I could get rid of, you know what? Let me try this here. Let me see if I can. Okay, no, good. All right, so let's look at a couple of examples. The first one says a teacher is trying to do an experiment with his or her students. And in order for this to be done, oh, it's a her, okay. So in order for this to be done, she has to divide this much sulfur among all her students, and the number of students will be 21, right? So the question is asking how many grams each student should receive. So this is a very easy calculation. We all know what to do, right? Basically, you're going to divide the mass by the number of students, right? So the mass, total mass is 453.6 grams. And we're going to divide that by 21, right? Now, in order for us to round off our answer correctly, we firstly have to identify what type of numbers we're dealing with here. Are they measured numbers or exact numbers, right? Now, the 453.6, what type of number is that? Measured, because that's the mass of the sulfur, right? What about the 21 students? Exactly. So basically, because this is measured, this has 4 sig figs, right? And because this is exact, this has an infinite number of sig figs, right? So what does that mean for the final answer? To what extent would you round off the final answer? To what?
Forcing
Exactly, right? So whatever you do on the calculator, whatever answer you get, you have to round off to 4 sig figs. So I'm going to take the 453.6 and divide it by 21, right? And I got, now this is interesting because what I got here is 21.6 grams per student, right? That is directly from the calculator. But as he just said, right, you need to express it to 4 sig figs. As we have it now, that's 3 sig figs. So how do we express it to 4 sig figs? Anybody? Exactly, you add a zero. So that's 21.60 grams of per student, I'm sorry, grams per student. And that's how you deal with situations like this, all right? Okay, any questions about this one? Any questions? Any questions? Okay, now in the case of the second one, basically you just ask to do this calculation and give you an answer to the correct number of sig figs, right? Now remember, whenever you're adding and or subtracting, you round off according to the lowest number of decimal places, right? So what you have to do is look at the number of decimal places expressed in these numbers. So how many decimal places do we have here? 3. How many decimal places do we have here?
2.
And how many decimal places do we have here? 4, right? So whatever answer you get here, you have to round it off to 2 decimal places. Exactly. So let's do that. 49.146 plus 72.13, and then I'm going to minus 9.1434, and I got 112.1326 meters. So we need to round this off to what? 2. So that becomes what? 0.13, exactly, meters. And that's how you do that, right? So those are just 2 simple examples, but this is basically what you have to practice doing whenever you're doing any calculations. Basically, I would say probably where I've seen students in the past making errors when it comes to these kind of calculations is that they incorrectly identified exact numbers as measured numbers, right? So you have to read the question carefully in order to understand, okay, is this number given? Is it a measurement? If that's the case, then you have to take the number of sig figs or decimal places into account. But if the number represents an exact quantity, like the number of students or like a defined number and so on, then you have to take that into account as well. And when it comes to defined numbers, usually, well, we talk about counting numbers, but usually when you have relationships within the metric system, like if you're going from metric to metric, right? Then the numbers involved as you go from one to the other, that would be exact numbers. If you're going from non-metric to non-metric, you know, like pounds to ounces and so on, those are also exact numbers involved. So non-metric to non-metric, these are all, or both types of transitions are exact transitions, right? Now, if you're going from metric to non-metric and vice versa, then these are non-exact, all right? So you have to take into account the numbers involved in this transition with respect to sig figs. But there's one exception to this. So let me write this down here. And the exception to this is the relationship between the centimeter unit and the inch unit. I had that wrong. Hold on 1 minute. That is not quite correct. 1 inch is equal to 2.54 centimeters. This is an exact relationship, even though you're going from non-metric to metric or vice versa, right? But all other relationships where you're going from metric to non-metric or the other way around, those are not exact relationships. So you have to take that into account when you're doing calculations involving those types of numbers. All right. We have 8 more minutes left in this joint. Any questions about this? Any questions? Any questions? Okay. You know what? I think I'm going to stop here because I don't want to start this topic and then stop in the middle of it. So I'm going to call it a day today at this point. If you came in late, make sure you write your name on this sheet. I forgot my class list. So I'm just taking roll this way. So make sure you sign that sheet before you leave here today. All right? And, see if I can see this down. Yes, ma'am.
Yeah, I'm saying because I didn't know we had.
Oh, okay.
So I had to go to my chem lab teacher
Mhm.
and I asked him, I was like, do we have a room for like this course? Cause when like before it started, it didn't show.
Yeah.
So he was like, yeah, he's like, this is the room and then this is teaching. I had you last semester, so I'm not too, I didn't know you were.
Right.
I was like, okay. He's like, just show up on Friday because I was like, I was looking on it.
Oh,
and I
okay.
was-
Yeah. Yeah, there was a lot of last minute
Yeah, that's what he was telling.
right stuff. Some miscommunication took place, which resulted in the course not showing up with a classroom. But in terms of what you meant, we started chapter 1, but before that, we went through the syllabus.
I was reading.
What's that? Okay, that's good. And I also showed where stuff is located in Canvas. I have posted, as you probably can see here, I think I have the date here wrong. Hold on, let me check this here. I've posted the videos. I haven't mentioned this in the syllabus, but I'm going to record all the videos.
Okay.
I mean, all the classes.
Okay.
And let me just check something here. Okay, so I think I remember what happened. I did not record this class because of the same confusion. I wasn't prepared to record it. But I've posted, I'm teaching another section, right? So I've posted that video in Canvas. So if you go, ooh, come on, get yourself. If you go to modules, which is down here, then you're going to see the videos posted here. I also posted some past videos as well. So we're not finished with chapter 1 yet, so you can actually get ahead in terms of, topics like this one, which we're about to do. And that's pretty much it. If you watch the videos, then you will get caught up.
And for the assignments, is there like a certain tab we go to download them or?
Well, what I'm going to do is I'm going to bring the assignments to class, and then we're going to work on at least some of the questions in class.
Okay, so we haven't had an assignment.
No, not yet, not
Okay.
yet, right. And then you would have to submit it electronically by a certain date. I'll let you know exactly what the due dates are. And that's pretty much all that we have done so far.
Okay,
All right,
thank you.
no problem. Okay, for you guys.